Wastewater that contains oil-water emulsions is usually found near the industrial processes such as petrochemical, food industry, and metal furnishing industry. The pollution of oil often occurs during its production, transportation, storage, or during usage in industrial processes. The oil spill pollution on wastewater has caused several effects to the human, environment, and living organisms. Some of the effects on humans, such as affecting the water sources and lack of clean drinking water. Meanwhile, the effect on environment include the pollution to water body and possible blockage of sewer pump and filters. The pollution also reduces the dissolved oxygen, in which endanger the habitat and life of living organisms. Various methods of solving the oil spill issue in wastewater, which can be categorized as physical, chemical, and biological methods. Passive measures using oil plumes function as to restrain the dispersal of oil contaminants over the water body. Other than that, dispersants are chemicals that are sprayed on a surface oil slick to break down the oil into smaller droplets. And biological method is a method that uses the microbial metabolism to break down the organic pollutants to harmless substances. However, the methods are cost-ineffective, toxic and hazardous, less efficient, high energy consumption, and difficult in operation. The oil adsorbent function to absorb the oil when brought into contact with the contaminated water. Oil spill removal through physical adsorption using the porous material has shown to be promising and efficient in removal of oil and organic pollutants. This method is not limited to oil floating on the water surface but also the oil droplets. Adsorbent also can be categorized into organic, inorganic, and synthetic. The example of organic sorbent materials such as rice hulls, straw biomass waste, and lignocellulosic biomass. Meanwhile, inorganic material includes zeolite, activated carbon, and aerosols, and for synthetic adsorbents such as polyurethane foams and polypropylene fibers. The natural sorbents are advantageous in terms of cost and it is inexpensive material and high biodegradability. However, most natural sorbents have low absorption capacity. Next, although inorganic adsorbents have high porous structure, it has low sorption capacity and unable to educate the buoyancy retention. Thus, excellent properties of adsorbent can be found in synthetic sorbents as it have high rate of oil adsorb capacity, oleophilicity, hydrophobicity, reusability, and biodegradability. The study focused on nylon 6 fiber synthetic sorbent. Nylon 6 fibers have portrayed special characteristics such as high in mechanical strength, chemically and thermally stable, low cost, and abundance in production. Moreover, the poly-glycidyl methacrylate (PGMA) grafted nylon 6 fiber was also studied. PGMA have excellent mechanical strength, resistant in acid and base, and easy in forming porosity. Thus, it is suitable for producing a good adsorbent. The objective of the study is to evaluate the suitability of nylon 6 fibers from industrial textile waste and its grafted PGMA counterpart prepared by radiation-induced grafting for adsorption for oil spill under treatment time. And the scope of the study is to analyze the performance of nylon 6 fiber and PGMA grafted nylon 6 fiber adsorbent through treatment time parameters with different types of solvents. In this experiment, nylon 6 fiber and PGMA grafted nylon 6 fiber will be used, and also three different types of solvents will be used, which is benzene, xylene, and toluene. Firstly, the initial weight of nylon 6 fiber will be measured and recorded using analytical balance. Then the oil-water mixture will be prepared with 10 ml of desired solvent and 25 ml of distilled water. Then the original nylon 6 fiber will be placed into the oil-water solution for 50 seconds and will be mixed with magnetic stirrer at 150 rpm. The wet nylon 6 fiber will be drained using the tissue or filter paper, and the final weight will be recorded. The step will be repeated using different contact time, which is 30, 45, 60, and 75 seconds, and the experiment also will be repeated with different solvents. The oil sorption capacity will be calculated using the formula shown. The three graphs shows the result of an experiment on sorption capacity against treatment time of toluene, benzene, and xylene. The figures shows the sample image of original nylon 6 and grafted nylon 6 adsorbent obtained from scanning electron microscope SEM, in which can be seen have different diameter after grafting, and the changes of chemical structure of nylon 6 fiber can also be evaluated through the Fourier transform infrared FTIR results. Overall, nylon 6 fiber has high absorption capacity compared to PGMA grafted nylon 6. Oil absorption capacity also shown that each adsorbent on the solvent has increased with increased treatment time. The highest absorption capacity of nylon 6 and PGMA grafted adsorbent for toluene and benzene is at highest treatment time 75 seconds. From the result, it can be proved that nylon 6 have high absorption capacity due to its oleophilic and porous structure. Besides, nylon 6 also has polar amide group, which have strong interaction with polar solvents. The amide-amide hydrogen bonds that give nylon good mechanical and also thermal properties. The PGMA nylon fiber might be affected by this feature and show low absorption capacity since the capacity of sorbent has filled up with water, which is polar solvent, thus making it have low absorption capacity compared to nylon 6 fiber adsorbent. In conclusion, the result shows that nylon 6 fiber has important criteria needed as adsorbent, such as good mechanical strength, high porosity, high absorption capacity, chemically and thermally stable. In future, the existing adsorbent material can be improved with the combination with physical, chemical, or biological treatment. This is to ensure the high regeneration of adsorbent and reduce the discharge of sorbent material after usage. Thank you.